Alright guys, so today we're going to be talking about merging leftist heaps. Now, this is the pseudocode for merging leftist heaps. It looks very complicated because I wrote it as shortly as I can, but there are a lot of little things in here. So you can look at the pseudocode if you want and pause and take a look at it, because those are the instructions. But right now I'm just going to get right into it. There are basically 3 steps to this. The first is going to be to merge the trees. The next is going to be to label the trees with numbers. And the last one is going to be to rotate the trees. So these are the 3 steps that we're going to do, the overarching steps. And we're going to go through it real quick. I apologize for the audio quality, by the way. I don't have the best mic, but hopefully you can still hear me. So all we're going to do is we're going to look at 80 and 40, just the 2 roots of each tree. And we're going to look at them. We're going to say, we're going to start with the left tree being the biggest. So we say, is 80 less than 40? No. Okay, so we go down, we march down the right-hand side of the tree. We're going to keep going this way. We never go this way. It's always going to be the right-hand side. Okay, so basically, we're going to march down. We're going to say, is 60 greater than 40? I'm sorry, is 60 smaller than 40? No. Is 32 smaller than 40? Yes, it is. So we pull out all of 32 and set it aside. And we stick the entire subtree of 40 right in here, just like this. Okay? So, we've got 40 now stuck in here. And then we do the same thing all over again. So we say, is 32 bigger than 80? No. Is 32 bigger than 60? No. 32 bigger than 40? No. Is 32 bigger than 36? No. So we stick it on the very end down here in a new slot, right like this. Perfect. So now we're done with the first step, merging the trees. We have to go on to the next step though, and that's labeling the trees. So labeling the trees works like this. What you're trying to do is you're trying to see the fastest way for each node to get to null. Now null is going to be defined as this invisible thing. We're going to write it in here just for clarity for 1 or 2 examples. But this is null. Okay, so it's going to be off of the end of every tree. So this is an end, which is null. This is an end, which is null. But also important to note, it's not just this that would be null, or this, but also right here. This is going to be tricky in this problem. You're going to want to watch this spot closely. But this is also a null, because there's a left tree, but there's not a right tree. Okay, so let's back up a couple examples, and let's get rid of this guy, and this guy, and this guy. I'll keep these here just for visualization, but we're going to basically look and label them as to which ones can get to null and how fast can they get there. Well, actually, how fast can all of them get to null? So we look at 32. 32 is at null, so we mark it as 0. 36. Well, 36 is going to have to go to 32, and then it'll be at null. Okay, so that means it'll have to be 1. Now 38, this is going to default to being at null. And 40, now we're looking for the fastest way for it to get to null. Now we could take this way and go to 36, which would make it 1, and then 32, which would make it 2, and then it'd be at null. And that'd be a 2. However, we're looking for the fastest way, which means we could take the left-hand side and go just 1, and then we'd hit null. So we're going to go that way, and that means that's a 1. Now here's the tricky thing. We're going to look here, and we're going to say, what about 5? 5 is going to be 0, because null's right here. But when we go to 22, normally we'd say, okay, we got to go 1, and then we'd hit it. So this will be 1, right? No, wrong, because there's actually an empty slot right here that is null, which means this also is a 0. Okay, now that's sort of the only real tricky part to this that you got to make sure you watch out for. Okay, so that's a 0. And then we say, what's the fastest way for 60 to get to null? Well, we could go this way, which would be 1, and then 2, and then it'd hit null. Or we could go this way, which will be even faster, 1, and then it hits null. Okay, so that means this guy will be 1, and these ones will default to 0, and this is going to be 1, and this will be 2, but really and truly it doesn't matter, because the root doesn't matter. Okay, so now we've done the second step, and really the most complicated of all of the steps, and that'd be labeling it. Okay, so now we're going to get rid of these guys, and all we're going to do is we're going to look and see which ones we have to rotate. Now to figure out what we have to rotate, all we have to do is look and see if the right side is ever bigger than the left side on the same level, then we have to switch it. Now we look at this guy and we say, is 0, we look at the 8 and we say that has a 0, we look at the 32 and that has a 0. Now they're both on the same level, and by level I'm talking about these. So we've got 1, 2, 3, 4, and obviously 5 levels in this tree. So what we do is we look at 0 and 0, and it turns out 0 is the same as 0, so we don't have to swap anything here. Whoop, sorry about that, guys. Now if we go here and we look and we say that 1 is actually greater than 0, so we're going to have to do a rotation. Now if we go to 5, you don't compare it to anything, which means this is good as is by itself. So long as it's on the left-hand side, it'll be fine. If the 5, however, was over here, then we'd have to swap it. So the 5 will default to being over here in most cases because it should have started as a leftist tree. But just for future reference, if that is the case, you know what to do. So basically it should always be on the left-hand side in this instance. Now if we go up here, we look at 22 and 40, turns out they have to swap as well because the right-hand side is bigger than the left-hand side. 1 is bigger than 0. If we go over here, 0 and 0, we don't have to swap. We go here, 60 and 35, so basically 1 and 1. We don't have to swap those because they're fine. And like I said, the root really doesn't matter anymore because we've already merged the trees. So now we know we have to do 2 swaps, so we're going to do them. It looks like this. All we're going to do is we're going to take everything in this tree right here, and we're going to put it right where this one is. So we'll move it to the side for a second, and okay, so we'll put this guy right here, and this guy is going to go right here, just like that. So that's swapping it. So we don't just swap the numbers, we swap the entire tree. And we have to do it one more time right here. And so we're going to take this whole thing and swap it with this whole thing. Now it's important when swapping, when I move this over, look what happens. The left tree stays left. So the 5 stays on the left-hand side of 22. The mistake a lot of people make is they'll take the 5 and they'll move it over to this side. That's a very common mistake that happens all the time. Don't do that. You will lose points because it's no longer a leftist tree. Okay, so we've got that now, and we're going to insert the 40 where the 22 was. Now if we look at our numbers, we can actually tell that this is now a leftist tree because 0 is bigger than, or because 0 is greater than or equal to this, 1 is bigger than 0, 1 is bigger than 0, so on and so forth. It all matches, it aligns. So that's the first example for a leftist tree. These take a little longer, but that's the third and final step for a leftist tree. Hopefully that made sense to you guys. I'm going to do a couple more examples and just really make sure you guys get it, so be sure to watch the next couple of videos. Thanks for watching. Have a good one.